Yeah. Oh yeah, you can't tell me what to do.
Yeah, just email that video to her.
It's like the missing students, the students who just disappear one day and never show back up, and I still think, well, maybe they're dead, maybe it's that they didn't show up. If they didn't show up because they're doing something else, they didn't show up because they can't. And then I think, I don't want to fail a student who's died. It just seems wrong.
Well, then just pass everyone that stops showing up.
Well, that's an option, but that doesn't feel right either.
We'll be teaching a lot of empty classrooms, I think.
Mm-hmm.
I think it was Thorsten Veblen, who was a college professor and economist. I think it was Veblen, who the students would automatically, were going to get a C in the class, unless they asked for a higher grade than they'd get whatever they asked for. There's definitely an advantage to that.
What subject was that?
I think it was economics. Economics, but they can ask the same test every year, would change the answers. All right. Now you've had some experience with capacitors already. So let's talk a little bit about notation here. We're going to start to be using symbols here. The symbol I'm using for capacitor is abnormally large. Typically, if I were doing the capacitor hooked up to a DC power supply, I would draw it like this. When they are the same length, this is the symbol for a capacitor. When you have them at different lengths like this, this is a power supply. Now, this specifically is a DC power supply, a direct current. We will get into alternating current later on in the semester, but for right now, when I say direct current, that the electrons or current flow, electron flow and current flow are opposite directions, is always going in the same direction on average. Whereas alternating current, the electrons are moving back and forth. Now, this has disturbed some of the students I've had in the past, the ones who have dealt with this on sort of,
The main person did it through the military. Just make sure I am actually recording.
technically, if I've got one of these things, this is a power cell. That if I want a battery, I need more than one power cell. So however many I've got, typically I see 2 or 3 for the battery. Technically, these are batteries. Now, I will typically do just one of them for a battery, even though officially that's not true. So that is good for everybody except for the few of you who actually get into, I guess, the electronics aspect of it. Just recognize that, yes, you can look back and go, that physics teacher I had did only one power cell and called it a battery. What was he thinking? Blame it on emotional scars from my childhood. So, battery. So, if you are dealing with a battery, most of you, I am willing to bet, have actually touched a battery in the past. If you have not, let me know, and I will hand you a battery so you can touch one.
What's a battery?
Actually, to define one, it's a device which holds. Would you like me to show you one? I assume you were joking, however, I shouldn't necessarily assume that.
I was joking.
Okay. And then when I do that, I'm thinking, wait, I came across like a literalist just then. So it's a device which contains energy in the form of chemicals. I'm trying to think what the official definition is. Not that you were necessarily asking for it, but I'm suddenly thinking, what is the official definition of a battery? It's something that will allow converting energy into electricity. So batteries have a positive and negative side. That's where I was heading a couple minutes ago. There's a positive and negative side. So I look at this battery here, and one of these represents the positive side, and one represents the negative side. Here's the memory trick. A plus sign takes twice as much ink as a minus sign. The plus side is the side that is bigger, that takes more ink. This is the positive side, and this is the negative side. The electrons, do you suppose, will come from which side? Yes. So the electrons are going to come from this side over here, and they're going to start flowing around. Now, if I don't have a capacitor there, if I just have a battery hooked up to itself, then I will have electrons flow all the way around onto the positive side. Unfortunately, when they were first setting up the conventions, they had no clue about electrons. Benjamin Franklin thought of it as a fluid, thus the term current. And he is, and in nature, if you have a hill with a water current flowing on it, it flows downhill. And so I've got a high potential side and a low potential side. And so he had current flowing this way. Later on, they figured out, oh, it's actually the electrons that are moving and they're going in the opposite direction. But they didn't change. So current, symbolized by the capital I, I should say DC current, symbolized by the capital I. AC current would be a lowercase I. Current flows from positive to negative side, opposite electron flow.
Is there a reason they didn't change it?
And it's probably in too many textbooks by then, and they said, yeah, we're just gonna live with it. I can't remember when they eventually figured out electrons. But Ben Franklin was doing his work, late 18th century, that whole 1776 around there. I think actually before, he did most of his scientific work, I think before the revolution. Because by the time he got to France as our ambassador, I think he was hailed as a great scientific mind. Some textbooks will talk about electron current and indicate the way the electrons are flowing as opposed to traditional current. Typically, if you just say current, you're referring to traditional current. So if I throw a capacitor in here, I have electrons coming out of the negative side here. They're moving around, and an electron shows up on a plate. Well, if I have an electron showing up onto the plate here, it's going to force an electron off the other plate. And so what we end up with is a negative one shows up on this side, and we lose an electron on this side, which then continues flowing on. Then another electron shows up here, and another one leaves here. And given enough time, we get a bunch of electrons on this side, and a bunch of positive charges on this side. They should be, the total charge on the two plates should be 0. They should cancel each other out if they touch. And also recognize that the more electrons I get on my plate here, the harder it is to put another electron onto it. It takes more and more effort, more and more energy to put another electron there. But ultimately, we end up with a plate, 2 plates of charge Q and negative Q, assuming Q is a positive number. We will also make the assumption in our nice ideal world here that these plates are large compared to the gap between them. So if this gap here, and I will use D for the distance between the gaps, if my plate, and we'll just assume square plate for right now, so if this is an L by L plate. So if D is much less than L, generally 10% rule, if D is less than 10% of whatever the length or width, whichever way you want to call it, then plates are considered infinitely large. For the space around them. You know, if I'm standing over here, like when you're doing your experiment, you had those plates really close to each other, really very tight distance, so we consider them to be essentially infinitely large compared to the space right in between them, mainly, or just outside of them. Let's flash back. I have an infinite plate here. What is the electric field? And let's assume it's some charge Q, evenly distributed across the plate. What is the electric field just outside it?
Sigma over 2 epsilon naught.
Is it 2 epsilon naught?
Yeah.
Epsilon's a naught, assuming we've got basically a vacuum right outside of it, or air is close enough. So if I've got my two plates here, I've got my positive plate, negative plate, what do we know about the electric field in relation to a positive plate? If I say positive charge, would that make a difference?
Goes away from it. It goes away from it.
Yes, indeed. So in my plate here, my positive plate, I've got my electric field going away from it. What about in relation to my negative plate? Therefore, what is my total electric field out here?
0,
What's my total electric field out here?
0,
In the middle?
twice,
So in the middle is just sigma over epsilon sum naught. So in our nice ideal parallel plate capacitor, the electric field just outside is 0, and in the middle it is sigma over epsilon sum naught. So let's go through and let's assume I've got 5 times 10 to the 9th coulombs on the positive plate and negative 5 times 10 to the 9th coulombs on the negative plate. Let's make the plates 10 meters by 10 meters. What is the electric field in between? Well, sigma is the charge divided by the area. So this becomes negative, actually, when you're doing this, let's look at the positive one. So 5 times 10 to the 9th coulombs divided by 100 square meters. So 5 times 10 to the 7th coulombs per square meter. So the magnitude of my electric field, or my electric field goes to the right, that's my positive and negative plates, is going to be 5 times 10 to the 7th coulombs per square meter, divided by 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared. Yeah. Oh. No, that's right, negative 12. Oh, God. I was thinking, we're getting an awfully huge number there, but that's because I made my charges incredibly huge. I hope it's not gonna be too inconvenient, but let's try to have some sense of realism here. Let's make that negative 9, negative 9, negative 9, negative 11, negative 11. Hey, what's a factor of 10 to the 18th power between friends?
I got 5.65.
So 5.65
Yeah.
units?
Newtons. Oh, it's newtons over joules.
Yeah. You could go through the units here and see that you get that, or it's electric field, we'll deal with SI units. Questions to hear? So now if I make the distance between them, my D there, so let's let D equal, well, it has to be under a meter there, but let's make it 0.1 meters, so 10 centimeters. So 1% of the length and the width of those plates. What is the change, what is the potential difference between the plates? Well, that's something that we did not too long ago. My electric field is considered constant. So my change in potential is just negative E dot delta X. Make that negative a little bit more obvious. So when I'm trying to find the potential difference, I do need to specify, am I going from the positive to the negative plate or negative to the positive plate? Yeah, it all depends on the whim of the question at the time. So let's go in the direction of the electric field. So what is delta V going from the positive to the negative plate? Well, my electric field is in the same direction as I'm moving. So E dot delta X will be a positive number, and then that minus up front changes it. So delta V is equal to negative 5.65 times that's newtons per coulomb, times 1.1 meters. We get negative 0.565 units.
Newtons times meters over coulombs.
All right. Which is negative 0.565 what? Volts. Newton meter is also a joule, so it's joules per coulomb, which is also a volt. So if I take my capacitor here, questions before I strap on a battery?
So where's the bottom, that 8.85?
That is the value of epsilon sub naught. The permittivity of free space, it's a concept. All right, so if I have a battery here hooked into my capacitor defined by this right here, what is the potential difference of my battery? What's the voltage of my battery?
Should be that. Should it be that?
Yeah, typically for voltage of battery, you just give the positive of it, but that's not which way you're going. So my voltage of my battery would have to be 0.565 volts. Let's think about why that has to be true. I have a point in space here which I say has an electric potential of 3 volts. I have a point in space here which has an electric potential of 4 volts. If I'm going from there to there, what is my voltage between those 2 points?
1.
Do the whole thing.
Volt?
There we go. All right, so my voltage is 1 volt. Suppose I'm going from 4 volts to 3 volts. What is my voltage?
-1 volt.
Okay. Suppose I start here at my 3 and then I cruise around, do a couple of loops, end up there. What's my voltage now?
1 volt.
Suppose I start at 3. Do a couple loops here, hit 4, keep going, do a couple more loops, and end up back where I started. What's my voltage now?
0 volt?
So, no matter what path you take, if I end up back where I started, the potential gains and losses should balance out, and there should be no potential difference between any point and itself. So let's think about the battery. I start here, and I cruise around the circuit, and I end up back here at the exact same spot. I know my total voltage between that point and itself is 0. I gain some potential going across my battery, because I'm going from a negative to a positive here. So that's going to be equal to the voltage across my battery. Then I come along to my plates here, that's my positive and negative plates, and I'm going across the plates, because again, I'm traveling along this path here. I go across the plates from the positive to the negative side, so my voltage is negative, plus V of the capacitor, which is delta V across the battery, plus negative 0.565 volts, and therefore my battery's got to be 0.56 volt battery. What I've just demonstrated is known as a Kirchhoff rule. And every single semester, I have to double check to make sure it's 1 H or 2 H's. Is 2 H's, okay. Now the textbook puts Kirchhoff in chapter 29, but we're going to exploit it anyway. So Kirchhoff voltage rule around any closed path. In other words, you end up where you started. The sum of the voltages is 0. I guess closed path, I just put a little circle there to indicate the closed path. This is sometimes known as the loop rule. So I'll put in parentheses here, loop. And while we're here, let's go ahead and do the other one. Kirchhoff's current rule, or junction rule. At any point, the total current in is equal to the total current out. Now, potentially you see something that contradicts it that we've done within the past couple minutes, but it does eventually get resolved. So I'm going to point out where it potentially contradicts, but I'm also going to point out that it does get resolved, and this leads to a huge breakthrough. If I have a battery here hooked into a capacitor, I talked about that the electrons leave the negative side, cruise around and get an electron onto the left plate, and an electron leaves the right plate, leaving a positive charge behind. So if I think about the capacitor as one unit here, I have electron flow in, electron flow out. Or going the other direction, current flowing in, current flowing out. However, if I narrow that look down to just this plate right here, I have a charge flowing onto that plate, and I don't have a charge flowing off that plate. So on the surface, it appears to contradict this. However, we will resolve that. And so for right now, I'll just assume current on, current off still works here. But yeah, this leads to a huge breakthrough done by Maxwell. All right, questions to hear? So I got my capacitor hooked up to a battery. I know if I only have just the capacitor, the voltage of the battery should match the voltage plus or minus the voltage of the capacitor, depending on which way you're going. Same with the battery. So let's just run through. I got a 12-volt battery here, hooked up to a capacitor. Let's make the capacitor 0.1 meters by 0.1 meters. And let's make the distance between the plates 0.001 meters. And inside here, we'll just assume it's air. Which is close enough to free space. What I want to know is, what is the charge on the positive plate? Sort of reverse of what we just did. All right, so what's the voltage across the plates of the capacitor?
-12.
Depending on which way you go. All right, so going from the positive to the negative plate, voltage is negative 12 volts. Okay. As long as it's hooked to the battery, the capacitor will have the same voltage as the battery. What is my electric field?
Sigma over epsilon sigma.
Except, well, I don't know what sigma is. We've got,
Oh,
I guess I just erased it.
the vex.
Yeah, the Vex equation. That should be equal to the negative E dot delta X. Which is negative E times 0.001. Because that delta V there is across from one plate to the other plate, it's not to halfway. So the magnitude of my electric field is 12,000 newtons per coulomb. And that's equal to sigma over epsilon sub 9. Which is sigma over 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. So what's my current density?
Q over A. charge over area.
Oh, yeah, I was looking for the actual number.
Oh, okay.
Yeah, that's the next step.
Uh, 1.062 e to the negative 7. Coulombs over meter squared.
What'd you say?
Is it coulombs over meter squared?
Yep. And that, as Precious mentioned earlier, is just Q divided by the area. And the area of the plates, that's Q divided by 0.01 square meters. And so Q becomes 1.062 times 10 to the negative 9th coulombs, or 1.062 nanocoulombs. Suppose, oh, questions up here? Suppose I wanted to double the charge on the plates. What can I do? Assuming I could change almost anything.
Area of the plates.
Okay. To what?
You would, make them smaller.
Did I say double the charge or half? Double the charge, right?
Yeah.
Okay.
You would make the area smaller.
Okay. So if I want to double this number, I can, cut that in half, keep everything else the same.